Okay, to differentiate this using the chain rule, we want to first write it in a more calc-friendly form. And to me, that means writing it as a power function. Okay. And here I have a very clear inside and an outside function. Inside, we've got x squared plus 3x minus 5, and then the outside function is to the 1/2 power. So I see here that I've got out of n of x. Okay. To take the derivative, the chain rule says I'm going to differentiate the outside function, leave the inside alone, multiply by the derivative of the inside. Okay, so I start here. I ignore what's on the inside, leave what's on the inside alone. So I'm bringing the 1/2 to the front, leaving the inside alone, reduce the exponent by 1. Okay, now I can put back the inside. Then I have to chain the derivative, multiply by the derivative of the inside, so 2x plus 3. These parentheses here are critical. If you leave them off, then you're just meaning times 2x, and it doesn't have the same meaning. So be careful with those. Okay, here I want to differentiate something which is a product of two pieces. I've got a first and a second, so I need a product rule. All right, and then when I go to differentiate the first or differentiate the second, it requires a chain rule. And one of the things you can learn to anticipate, when I do a product rule plus a chain rule, or a chain rule, or a quotient rule plus a chain rule, there are going to be pieces that can then be factored out. All right, what do I mean by that? Well, let's just go ahead here and try. So I'm going to leave the first alone, multiply by the derivative of the second. All right, and here's the chain rule. So I leave the inside alone. All right, then multiply by the derivative of the inside. Here's the plus that comes from the product rule. Now I have to differentiate the first times the derivative of the inside. And now I'm leaving the second alone. All right. Now if we look at this, there are a lot of common factors here. Okay. I have some 4t squareds plus 9, so I've got this and this term. 3 is in common on both sides. T cubed minus 4 on both sides of this plus sign. I also have a t on both sides. Right. So all those common things can be factored out. Okay, and let's see what's left after we do that factoring. This sort of simplification becomes important later on when I ask myself, or when we ask the question, where does G have a horizontal tangent? Right, that question is related to a lot of other questions that we want to answer with calculus. So for the 4t squared plus 9 terms, I have 3 of them here, and I should have 2 of them over here, a little error. So I can factor out the lesser of the 2, 4t squared plus 9 squared. T cubed minus 4, 6 here, 7 here, let's take out 6 of them. We're always going to factor out the smaller of the two exponents. The 3 is in both terms, so I can factor it out. There's 2 t's here and 1 t here, so I'll take out the smaller of the two powers, just t. And now what remains? Well, I took out 2 of those, so one of those is left. I did not take out the 7, so it's still there. Took out all 6 of these. We took out 3 times t, but there's still one more t. Plus, now this plus is the original plus from the product rule. Took the 3 out, took 2 of these out, took the t out, the 8's still there. Took 6 of these out, so the t cubed minus 4 to the 1 power. Now there's still a little bit more simplification that can be done, right? And that's here. If I FOIL everything out, multiply everything out, I'm just going to write parentheses because this is going to be a regular factor. I have 28t cubed plus 8t cubed is 36t cubed. 63t minus 32. All right. Now with this next problem, there are a variety of ways to do it. I can leave it in this form, or if we write it in the more calc-friendly form, as replacing the radical with an exponent, I can leave it like that. It's possible to do the differentiation from there. That's going to be a chain rule followed by a quotient rule. Or I can write this as, using properties of exponents, I can distribute the exponent onto the numerator and the denominator. Now I've got a quotient rule followed by some chain rules. Or, once I have it in this form with the exponents up and down, I can bring the denominator up with the negative exponent. Right. So pick your poison. Here we're going to have the product rule plus some chain rules. All three of these forms will work. Okay, let's see the first one. We'll label this 2 and we'll label this 3. Okay. In approach 1, we've got f prime of x. Okay. We have the inside alone, that's all of this, so we'll have 1/2 to the minus 1/2 times the derivative of the inside, which requires a quotient rule. Low d high minus high d low over low squared. Alright, now the devil's in the algebra. To get rid of a negative exponent here, I can take the reciprocal. Right, here I'm going to clean things up. I've got 3 minus x squared plus minus minus. Let's write it all out. 3 minus x squared. These two minuses cancel each other, so then I have plus 4x plus 2x squared. Okay. This first I'm going to split up by distributing the exponent up and down. Here we can do a little more cleanup, so you have x squared plus 4x plus 3. Now here I can cancel some 3 minus x squareds. Now I have just change the exponent to 3/2 power. I didn't cancel all of those. So all together now I'm left with and if you're happy with that approach, you can stop right there. Otherwise, let's look at form number 2. So in form number 2, we started by changing the look of our function to look like that. All right, now if I differentiate, I'm going to have to do a quotient rule followed by chain rules. This version might be a little bit harder to simplify. Low d high times the derivative of the inside, which is 1, minus high d low. So I'm going to get here times 1/2. 3 minus x squared to the minus 1/2 times the derivative of the inside minus 2x over rho squared. It's at this point that sometimes it can be difficult to think about how to proceed when we want to simplify. But kind of like when we did the product rule in the previous problem, when I do the quotient rule combined with the chain rule on the pieces, there are always going to be common terms that can be factored out. Notice here I've got some 3 minus x squareds on both sides of this minus sign here. I've got some 2 plus x's. And we're going to stick to our convention that when we factor out some terms, like this 3 minus x squared, 3 minus x squared, we're going to take out the smaller of the two. So I'm going to factor out 3 minus x squared to the minus 1/2 power. Similarly, I'm going to factor out 2 plus x to the minus 1/2 power. I can take out the 1/2, which is in both of these. Okay, so here I factored this out. We factor out the 1/2. This is just a 1, so it's along for the ride. Okay, I took out 3 minus x squared to the minus 1/2 power, so I have to leave some of these behind. Okay. And how many do I have to leave behind? Well, I'm going to adjust this exponent here so that when I multiply these two terms back together, I end up back at the 1/2 power. So that means this has to be the first power, because 1 plus negative 1/2 equals plus 1/2. Here's the minus sign that comes from my quotient rule. Same idea with the 2 plus x to the 1/2. I took some of those out and I have to leave some behind. And again, it'll be the first power because when I multiply these back together, I get 2 plus x to the 1/2 power. The 1/2 has been taken out. 3 minus x squared to the minus 1/2 has been taken out. And I still have a minus 2x here. And in the denominator, I should have 3 minus x squared to the 1/2 squared. If I take something to the 1/2 power and square it, I'm just back where I started. Now we can clean up what's in parentheses. We have a negative negative here, or in the brackets rather. And this is just as it was before. This will simplify to x squared plus 4x plus 3. Now I'm going to put this guy down here and this guy and the 2 also downstairs. I can migrate these things to the denominator by reversing the sign of the exponent. Right, if an exponent is negative, I can move it across the fraction bar here by making the exponent positive. So this comes down as 1/2 power combined with this 1 power gives me 3 minus x squared to the 3/2. And in the numerator here, alright, we're going to look at this one more time using the quotient rule to do it, or I'm sorry, the product rule, so form 3. So in that way, we took and rewrote this as 2 plus x to the 1/2 power times 3 minus x squared to the minus 3/2 power, minus 1/2 power. Then I'm going to use the product rule plus a chain rule on each of the pieces. So the derivative, leave the first alone, take the derivative of the second. I subtract 1 from the exponent there and I get minus 3/2 times the derivative of the inside by the chain rule. Plus, this is the plus from my product rule. Now I have to take the derivative first, leave what's on the inside alone, times the derivative of the inside, which It's simply 1 in this case. Alright. Now, very much like before, I have some common terms I can factor out. Right. So for the 2 plus x terms, I'm going to take out the smaller of the 2. For the 3 minus x squareds, I'm going to take out the smaller of the 2. So we're going to take out 2 plus x to the minus 1/2. 3 minus x squared to the minus 3/2. I can take this 1/2 out in both cases. Minus minus becomes a plus. So if we took out 2 plus x to the minus 1/2 power, I'm going to have to leave behind some 2 plus x's to the first power, so that when I multiply these back together and add the exponents, I wind up back at a half. Likewise, I didn't take out the minus minus 2x, so I still have a 2x here. Here's the plus from our product rule. Took these guys out of the way, took the 1/2 out of the way, the 1's along for the ride. I took out minus 3/2 powers of these, so how much do I have to leave behind? 3 minus x squared to the first power. If I multiply these terms together, minus 3/2 plus 1 by adding the exponents gives me the minus 1/2. And now we're just a short step to exactly where we were in the previous problems. Multiplying everything out here gives me x squared plus 4x plus 3. And these guys can of course migrate down. And I have this 2. Multiplying by 1/2 is the same as dividing by 2. Alright, wasn't that fun? That kind of algebra isn't really fun, but it's necessary, because as we go forward here, we're going to take the derivative of something and we're going to ask ourselves, where is the derivative equal to 0, for instance? I have no idea based on this expression where the derivative is 0. But once I get down to here, I can easily figure out where the derivative is 0, where the numerator is 0, or where the derivative is undefined by looking at the denominator. So that's an important skill. Right. Here we've got a chain rule. We're going to write this first in calc-friendly form. So I take the derivative of the outside, leave the inside alone, reduce the exponent by 1, multiply by the derivative of the inside. But the derivative of the inside here, the inside is a product, so to differentiate it, I'm going to need to use the product rule. So I'll leave the first alone times the derivative of the second, plus, take the derivative of the first, leave the second alone. There's not much more we can do with that, so that one's done. This is a double chain rule problem. This is not multiplication. This means take the cosine of the secant of x to the fourth. It's a composite function. If we start with the number x, we're going to take x to the fourth first. And then we're going to take that result and take it and plug it into secant. And finally, we're going to take that new result and plug it into cosine. Right. So each one of these in the chain is going to have its own derivative. The last derivative here will simply be 1, so we don't really see that one. But these other two, right, require 2 chain rules. Right, I'm going to use Leibniz notation here to try and illustrate where these chain rules come in. So we're going to take the derivative of y, so that's the same as taking the derivative of this stuff. According to the chain rule, I differentiate the outside function, leave what's on the inside alone, and multiply by the derivative of the inside. Okay, I'm all done with this. Alright, now this is just along for the ride. Now I can focus on taking the derivative of secant of the stuff. Well, again, that's a chain rule because secant has some crazy stuff inside of it. So the way I take the derivative of secant of something is the secant of that something times the tangent of that something. And then by the chain rule, I have to multiply by the derivative of that something. Okay, so there's chain rule number 2. And finally, I can differentiate, take the derivative of that x to the 4th, which is, that one's easy. At least I hope it is. All right, very good. On this problem, having that 2 right there can be confusing. It's convenient for writing trig functions. We know what this means. Right? But when it comes to differentiation and trying to figure out how to use the chain rule, putting the 2 next to the sign is kind of a bad thing to do. We'd be better off if we wrote sine of theta squared plus cosine of theta squared equals 1, even though that looks less familiar. Right? Because here it's very clear what's on the inside and what the outside function is. So we're going to do that here. We're going to take the sine of the tangent of theta squared. Right. So this is a composite function. Theta gets sent to tangent theta, and then I square that result, and finally I give that to the sine function. Okay. So I'm going to need to do the chain rule a couple of times here. Start with the outside function. Derivative of sine is cosine. Leave what's on the inside alone. Now I have to multiply by the derivative of the inside. This first bit is just along for the ride now. Derivative of something squared is 2 times that something to the first power times the derivative of the inside. Whew. Finally, the derivative of the last one here is secant squared, and now we're all done. Alright, this is a funny looking problem, but this sort of a problem is important because it makes us think about exactly how the chain rule works, but in a different way. Maybe that's a little more abstract, but it makes us identify what the important pieces are. Right. So according to this, f is my outside function, g is my inside function, and my definition of the chain rule tells me I differentiate the outside, leave the inside alone, multiply by the derivative of the inside. Well, I want to find f prime at minus 2. So let's plug in x equals minus 2 here. Okay. G of minus 2. Well, that's part of my given data. That's 5. G of prime of minus 2. That is 4. So I've got f prime at 5 times 4. And finally, f prime at 5, that's something I know. That's minus 7. Now notice I didn't use this, and that's just there to distract you, right? I don't need to know what f prime is at minus 2. I need to know what f prime is at g of minus 2. So we figure out what's inside here first, and then we plug that into f prime. So the answer is negative 28. Okay, I know what my point is. I need to find a tangent line, so I need the slope, which means I need to find the derivative and evaluate it at x equals 1, which is the x-coordinate of my point on the curve here. To find the derivative, I'm going to write this in the more calc-friendly form, and then differentiate. We start with a product rule. So I leave the first alone times the derivative of the second. Okay, 1/2 Bring the 1/2 to the front, leave what's on the inside alone, to the minus 1/2 times the derivative of the inside, plus. Leave the first alone. Sorry, we already left the first alone, took the derivative of the second. Now we're going to take the derivative of the first and leave the second alone. Now you can simplify this, but there's no need because all I really care about here is plugging in the number 1. So if you look carefully here for a minute, this is 1 over square root of 2 plus square root of 2. We'll rationalize that first one. So I've got 1/2 square root of 2 plus square root of 2 is 3/2 square root of 2. That's my slope. Point slope form. Right. This final plus square root of 2 comes from adding square root of 2 to both sides. So we're moving this minus square root of 2 over to the right side. Here I have 3/2 square root of 2 plus 1 square root of 2. So I can rewrite that as minus square root of 2 over 2. Good. All right, here we just want to take the derivative and apply it to both sides. Requires using the chain rule. Derivative cosine of something is minus sine of that something. Leave the inside alone, multiply by the derivative of the inside. Derivative of something squared is 2 times that something to the first power times the derivative of the inside minus sine of x. Minus, that's the minus from right here. 2, leave the inside alone, to the 1 times the derivative of the inside. Minus 2 sine 2x. So you have minus 2 sine x cosine x. Minus 2 sine x cosine x is minus 4 sine x cosine x. Divide both sides by negative 2, and we've got the double angle formula for sine. Should look familiar. It's one of the ones that you should have in your memory banks. How about proving the quotient rule by using the product rule? So if I write q of x for quotient equals f over g is f times g to the minus 1. And q prime of x, right, this is f times g to the negative 1. So I'm going to leave the first alone, differentiate the second. Right, bring the exponent to the front, leave the inside alone, reduce by 1, multiply by the derivative of the inside function. Plus, take the derivative of the first, leave the second alone. Right. This doesn't yet look like the quotient rule. All I've done so far is taken and moved the things with negative exponents into the denominator. But if I get a common denominator here, that's dangerously close to the quotient rule. Quotient rule is customarily written the other way around. Doesn't really matter. There we go. There's the quotient rule. All right, last problem. So the length of the day in hours on day T of the year is given by approximately by this function. If I want to find the rate of change or the slope of the tangent line at 265, I need to take the derivative. Derivative of 12 is 0. Pull the 3.28 out of my way. Derivative of sine is cosine. Leave what's on the inside alone. Multiply by the derivative of the inside, which is 0.0172. So evaluating this, make sure you're in radians mode. At day 265, and that comes out to be about minus 0.056 or so. Sorry about that, you just got treated to something on the screen. Hours per day. If we convert that to minutes per day, we're going to multiply by 60 minutes in 1 hour. That's about minus 3.4 minutes per day. So at this time of year, we're losing more than 3 minutes of daylight each day, or around the fall equinox. Thanks.